My name is Tommaso Calarco and I am a theoretical physicist. I am a professor here at the University of Cologne, and where we are having this wonderful conference, and I'm an institute director at Forschungszentrum Jülich. I work on quantum control, so that's the Institute of Quantum Control, and this is what I'm bringing in QSolid. So this is really between the hardware layer and the upper layers of the software stack, how we manipulate, how we tell the system, what it has to do in order to do those quantum gates in the best possible way. The German Quantum Initiative essentially would like to make us independent in terms of being able to make our own quantum computer, so that we don't just have to buy them from someone else, maybe outside of Germany, outside of Europe, and then just program it, but we really want to rely on these machines which we make here for a series of reasons: of economic independence, as we see with some events which are recently happening. It is good not to have always to buy essential goods from abroad, but also in terms of sovereignty and control on our data. A lot of the companies which, and several of them also in Germany, which are important users of these technologies, they are not so happy for their proprietary data about some very important processes in their production to be available outside of our country. And so QSolid is really addressing this in the sense of making, producing, building our own quantum computer, mostly focusing, of course, on the superconducting qubit technology, which is among the most advanced worldwide. As a matter of fact, it is the one on which a lot of big corporations in the US are betting and investing a lot, and we would like not to have to buy, as I said, a computer from Google, from IBM, and so on, but to have our own. And this is what QSolid is setting up, so that we will start having our own access to our own resources fully under our own control. It's very important to consider all these sides, because often when we speak about quantum advantage, which is the possibility of really performing some tasks of practical use which a quantum computer can perform but no classical supercomputer could attain, often we just focus on industrial applications. But as a matter of fact, among the first of these applications and this huge advantage, which I shouldn't no longer say will be coming, but is already coming, we already see that in science, in the field, for instance, of quantum simulation, a special application of quantum computing, we already see that there are results in which we use quantum machines to calculate properties of complex physical systems which cannot be calculated with supercomputers. And so it's very important to really consider that advantages will come in science and in business and in society. So in science, it will come with the possibility of attacking, of solving problems which at the moment are beyond the capability of, and also foreseeably in the future beyond the capabilities of classical supercomputers. And this involves not only the simulation of different physical models, Hamiltonian models, which are relevant for materials, but also it involves the simulation of chemical processes, for instance. It also involves aspects in more broadly in many-body theory, if you wish. This will be the first. For instance, one quantum computing specialized in simulation machine, which we will have here in our region, in Jülich, starting from next year, was already able, this is from a startup company, Pascal, in France, was already able to solve a specific model of magnetism in a way that enabled now theorists to take the results and to use them as a basis for very efficient simulation of even bigger systems, something which was not possible before, because the ansatz, the assumptions, the starting point for these future simulations could only be retrieved from the quantum computation simulation in this case. So, the science side is going to be very important, and we should really highlight because, you know, when we underscore the importance and validity of industrial applications, we should not lose sight of the fact that the foundation of all future industrial applications is always scientific research. And so the scientific impact is not something which is just a side note, but it is very much in the mainstream of the future benefit for quantum computing. Now, if we come to business, then beside the aspects which I just mentioned, which of course are not only of scientific interest, but directly also of industrial interest, you know, we can think, I mean, we had a meeting with Bayer, I think it was yesterday, yes, in which, you know, they explained to us how they are attacking problems in simple molecules which can be addressed on a quantum computer, and this is directly relevant then for their production. Not now, because it's still molecules which are very simple, but then as the complexity grows, as we are trying to, you know, enable, including with our QSolid project, then it will be possible really to tackle molecules which, you know, cannot be simulated otherwise, and this is something which then will feed into their production lines. Same goes with materials. For instance, Bosch has a remarkable group. I mean, I was very impressed recently because you talk to these people, including with Bayer, and they are from industry, but it is really, I mean, from the discussion, you couldn't tell they are from industry because they speak the same language of, you know, Hamiltonian models and complex systems and dynamics and eigenstates and so on and so forth. And they really are just theoretical physicists in industry, which of course work on that with the angle of using these results for, you know, their own economic interest. And so, but beside these aspects, there is also the whole branch of optimization, you know, which is for scheduling, for logistics. And actually optimization is also something which is very central, like finding minima. Optimization means finding minima of certain complex function. This is very relevant for neural networks as well. So for all the artificial intelligence and machine learning, this can have a big impact, and this is why a lot of companies in that field are also investigating applications. So this is the range of, for instance, just in terms of logistics, we have been contacted recently by DHL, who you know, is also located in the region, and they want to learn how you can use a quantum computer to optimize routes of like delivery parcels, for instance. So this is a broad range already, but actually part of the research that we are doing, and part of which we will enable also with the infrastructure, which is also part of QSolid in Jülich, and the infrastructure unique, is for giving access to users to the quantum computers that we are developing and others which are available, as I mentioned before. And this is really to broaden the spectrum of possibilities of problems that can be solved beyond those classes of problems where we know that quantum computers can be impactful, also beyond that, you know, going in other aspects. One aspect which I would like to mention, which is coming up recently, is the aspect of fluidodynamics, the simulation of you know, complex systems with partial differential equations, which you know, sounds very technical, but it has a lot of immediate application. You know, for instance, in you know, aerodynamics and how planes work. There was a couple of years ago an Airbus quantum challenge in which Airbus was you know, posing the challenge to any proposers about what can you do with a quantum computer to solve problems of aerodynamics which are relevant for flight. So this is for business in a broad sense. And for society, well, actually several people ask or think, okay, will we be able to get a quantum computer at home or in our pocket? And this is the first consumer electronic device which contains quantum technology. This is a Samsung Galaxy Quantum phone, which actually is not available in this country and in this continent. It's from South Korea, because South Korea Telecom has a majority stake in the European company which produces the quantum technology which goes in here, which is a 2.5 millimeter square chip which is generating random numbers, a quantum random number generator. nothing to do with a quantum computer. It's actually a component which can be used in a quantum computer, but it is not a quantum computer in your pocket. This is just to show that there are already some devices which we can carry with us, yeah? But not so with quantum computers. So with quantum computers, actually what we expect is that they will be available as a service, such as in my other pocket, I have another sort of more traditional phone, and I have an assistant there, and when I tell, hey Siri, do something for me, Siri has no clue, she sits in the cloud, actually, so my voice gets transmitted to some cloud service, and then the answer comes back. And so this is the likely way in which we are going to use quantum computers for the next and mid-term foreseeable future. They will be located not necessarily with supercomputing centers like here in the region and in QSolid, but they could be located in different places and be accessible by anybody in principle. And as we expand the breadth of the spectrum of problems that we can address, then this will mean that more possibilities will come for, everybody to use the benefits of this. But even if that should not be possible, or if that would not be easily realizable technologically, because this is the challenge that we are addressing, already society will benefit from the output of what we are doing. Because, for instance, if we are able to improve flight or energy transport, for instance, via quantum simulation, then it means that a lot of energy needs are going to be reduced. If we improve logistics, then it's clear the benefit that will come to society in terms of better services, and again in terms of reduced CO2 emissions and so on. So what we can achieve, what we already now know that with sufficiently big quantum computer we will be able to achieve, is something which will indirectly benefit society, and it is rather possible that more direct benefit will come as we extend the range of applicability. I would say that the complex of challenges that we have, they can be summarized under one keyword, which is engineering. In the sense that the physics, the basic science of what we are to do is essentially clear. But it is far from clear how we build upon this science in order to make scalable machines. So to increase the number of qubits to the size which is necessary to actually tackle effectively those problems which I mentioned, it is indispensable to really create those qubits, fabricate them, couple them in a quality and in a reproducibility and in a robustness which actually is completely beyond the current capabilities. So the main challenge, and it is actually a challenge which is not just for the QSolid project, but common to all the projects that we have in this demonstrator, quantum computing demonstrator call of the Federal Ministry for Research and Education, is really to make this leap to enable these engineering capabilities which will allow us to take off in terms of the number of qubits with the appropriate fidelity, with the appropriate quality. Because just having already now, we could, with the QSolid technology, produce a chip with 1 million qubits. And this would be completely useless, because those qubits, they need to be operated, all of them together, in like an orchestra. You can summon together 1 million people for the kernel carnival, yeah? But does that not mean by far that you can, you can give them an instrument and they will play 1 million people in an orchestra and you get a perfect tune? It would be a complete mess. So this is the challenge that we now have, create a structure, an orchestra in which all our many qubits all together play in tune. And this requires enormous progress on the material side, on the fabrication side, on the supporting technology side in terms of cryotechnology, low temperature, cryoelectronics, and so on. And also, as we go higher in the stack, engineering of the software, engineering of the firmware even, which is what, as I mentioned before, we do in my institute and also in Frank Wilhelm Mauch's institute. Engineering of the layer of control, which enables to get the best out of these qubits, and then compilation, which means how we best combine the different building blocks to go towards algorithms, and then quantum software engineering, which means how do we structure the best algorithms which, with a given size of the computer, extract the most benefit out of it without sort of wasting resources. So engineering at all these scales. And it is almost ironic that as a physicist I'm saying, oh, we need engineering, because we have been taught when I was young, a long time ago, that, we physicists, yes, we understand things, engineers, that. But we actually, the one main realization of this, our field of research, is how deeply wrong this is. And if you leave something just in the hands of physicists, that's hopeless. You really need to create this synergy with all the actors which can bring together all the components and the competencies to create this, packaged, efficient, integrated, and effective device.